Hopefully you remember the input stage. That was M5, the current mirror, M3, M4, and then here was an ideal current source. And this current source is now made as a simple trans admittance amplifier with a voltage reference. The voltage reference is made from the power supply with the resistor through, so you could also call this a current mirror, yes, but you see here I make it a low noise voltage reference, and that is often the case in integrated circuits, in low noise integrated circuits, that you want to have one pin available for a decoupling capacitor, because 100 nano you cannot put inside, to kill all the noise at this point and make this a low noise voltage that then is converted into a current. So the noise of this resistor R5 and this M7 is not relevant. And since you want to have a low current here, otherwise you're just consuming a lot of current, then you will also have high values of resistors and low values of GM, so high voltage noise. And that you want to kill. That's why this transistor is here. This is the output stage, and here R6 is the current through R6 is generating a voltage, and that is the floating voltage source that we know from before. So I tie the output of the first stage, M3, M6, to the input of M2, which is there, and not to the middle, because there's more voltage room here that you can see if you do the operating point information. And then you have here the, so this one is a voltage source, and there just here the complementary, parallel connection. How is this voltage generated? Well, I want about 1 milliamp in M2 and M1 together. So I create here a reference current and I scale all the devices, which means that if I take, for example, well, I don't know exactly what is the current here, but let's say it would be about 100 microamps, then the multiplication factor, or the width of this transistor, is 10 times larger than the width of this one, and this one, and this one is 10 times larger than this one, and this one, and this voltage is exactly what we needed to make 100 microamp here, 100 microamp here, and 1 milliamp there, because we have the same VDS. That is basically the whole idea. It is called a model-based biasing, and for people who are interested, it is discussed in the book. This is not part of your exam. The course ends with design biasing on system level, so with ideal sources, the concept of biasing. We are not going to ask you implementation of bias sources. I just want to show you this, because then you see you can end up with a complete design. Here you see the other floating voltage source. I create from this low noise voltage here, I create another current, and I direct this current through a resistor in order to create the voltage drop that I needed there. But as I said before, I tie the capacitor, feedback capacitance, direct to the output and not here, because otherwise I have a nonlinear attenuator here, because M12 also have a non-zero output, a non-infinite output impedance, and it is non-linear because of the capacitance and GM. So then I'm really introducing distortion. So 5 minutes to run a simulation. Which simulation they're on, I don't even know, but it was AC. So AC. So here is the Bode plot. And you see with the correct biasing and everything, it's about 2 gigahertz. As I said, 2 gigahertz minus 3 dB minus 3 dB is even 2.6 gigahertz, a little bit more than that. With an FT of the process, peak FT of 50 gigahertz, and not all the transistors, of course, have peak FT like this. You see, I made a little bit more complex phantom zero compensation because of poles that are added, but this is easy to tune, and let's say Cadence has all kind of automatic tuning equipment, so don't worry too much about all this fine tuning. This can really be automated. Now let's go for the next simulation, which is a noise simulation. Okay, so I'll run it again, and then I will do the noise simulation, and I will add traces VI noise. Okay, if you hate this color as much as I do, then we can do this, and we can attach a few cursors to it, and then we can go for 100 kilohertz, which should be below 10 nanovolt per square of hertz, and at 10 megahertz it should be below 5. And you see we have the values here. We have 4.3 and 8.45, so are well in the noise. So probably there can be a lot of optimization by changing the geometry of the devices to get better values. But this, as I said, you also have to do corner simulations, and not everything is modeled here. This is really to illustrate the structured electronic design, but not to sell an amplifier. Next thing we have is the transient analysis for the intermodulation distortion. Let's immediately put it to 800 nano. That's enough. And run it and plot the load voltage, and from the load voltage I want to see the Fourier transform, and maybe do a decent color and 2 cursors. And now we go to the right one. So let's say we pick this one for the input signal, and we take the highest one, because all IMD components should be below 50 dB. And here you can see that the distance is 52.3 dB, which is also well in spec. I cannot guarantee you that if you do temperature changes, etc., that everything will be in spec, but this was not yet the aim here. You see, in a structured design method, we are well able to come to a predictable solution that behaves according to spec, and that is ready for optimization. Because don't forget, there are now so many transistors in it. You can optimize from all these transistors the width, the length, and the operating current. And this you better automate with a good design goal. So probably here the noise doesn't seem to be a big problem. There's not so much margin in a non-linearity. So I would probably try some optimization for getting the best values for the intermodulation results.